In today's lecture, we are going to begin our long discussion of the geodesic equation, which really should be plural, geodesic equations. It's plural because it's a tensor equation, so you're going to see it has indices, and the different combination of indices is each a separate equation. But it's very common to call it the geodesic equation because you'd write it down as literally one equation. But this is a long topic, and it's an important topic because it goes back to a fundamental assumption of the general theory of relativity, that all objects in the universe that are in free fall, that are not subject to any forces, follow a world line that is a geodesic of the four-dimensional manifold that we call space-time. So that is an assumption. So I guess in this picture here, I might have some gravitating body here and a gravitating body here and here, some weird thing where this particle ends up sort of freely falling between these gravitating bodies, maybe ultimately, I don't know, even perhaps orbiting them. Very complicated. This is all spatial motion that we have depicted here now. But these paths here, are all geodesic paths through the space-time. And that is an assumption of GR. It's not provable, right? It's not something that you can derive. It's an intuitive axiomatic assumption. And it's intuitive because in the Newtonian world, where everything is, where gravity is a force that reaches out and space-time is purely Cartesian and purely metric in a totally Euclidean sense, we know that objects that are in free fall, uninfluenced by any force whatsoever, right? In the Newtonian system, an object uninfluenced by any force moves in a straight line. And it's the force of gravity which causes it to twist and turn in this example and circumstance. But if there was no force of gravity, it would move in a straight line. And those straight lines are, in fact, geodesics of flat Euclidean space. Well, I guess Euclidean, that's redundant, right? Euclidean is what we mean by flat in the context of Newtonian theory, where we're not dealing with a Lorentzian metric, we're dealing with a straight-up Euclidean metric. Time is a parameter that's completely separate from everything. But the point, but even if time wasn't, even if you made Euclidean, even if you used a four-dimensional manifold of space-time in Newtonian theory, you would still get a four-dimensional Euclidean manifold that was flat, and particles that had no influence of any forces, and gravity is a force in that picture, move in a straight line, which would be a geodesic of that space-time. So the idea is, well, we're going to now allow space-time to remain, it'll remain a four-dimensional manifold, but it won't be Euclidean, it'll be locally Lorentzian, right, by the equivalence principle. It's locally, well, the fact that it's Lorentzian is a discovery of special relativity, right? So space-time never really was Euclidean. So the fact that it's Lorentzian locally is special relativity. And then we, well, the fact that space-time is Lorentzian is the assumption of special relativity, which holds up by experiment. And then we, instead of saying it's globally Lorentzian, we say that it is locally Lorentzian, and then we allow it to not be flat anymore, but it's locally flat. And so we say that whatever that manifold is, we're still going to say that if you have no forces acting on the particle, it will move along a geodesic in that space-time. That's an assumption. And now gravity just goes away and is completely embedded in this non-flatness of the metric. Okay, so the geodesic equation is at the core of what general relativity is all about. And today we are going to derive the geodesic equation using one particular method, a mathematical method just that's purely mathematical reasoning. And then in other lessons we'll use a couple different methods to derive the geodesic equation. And we'll spend some serious time on this. So the mathematical derivation, what I mean by that is we are just going to be talking about four-dimensional manifolds and the calculus on those manifolds using the idea of infinitesimal movements around coordinate systems. This material can be reassembled from a textbook of D'Inverno's textbook, and plus a little bit from Chandrasekhar's textbook. I've kind of made a blend of these two, actually. I don't think either one attacks it with perfect clarity. It's doubtful I will either, but the point is blending these two together, I think, is the most important way is the best way to get through it. So we begin with a curve in space-time. That curve is going to be called gamma. The parameter of that curve will be lambda. And every curve will have a velocity, which we will call gamma dot of lambda. And that velocity is defined as the derivatives of the curve with respect to the parameter, and it's a vector. So there is our coordinate system basis vector on the right side. And this is a very critical place to start. You'll notice there's a few things. One is that this is a function of lambda, and in fact, it's fair enough to say, well, you know what, this should either be boldface, like that, right, or, and then this would be boldface too, or we should write that as gamma dot mu of lambda, indicating that we're dealing with purely the coordinates, right? One way or another, we have to show that there are 4 different components to this thing. And this is the usual kind of curve, right? We have lambda, which is on the real line, and there's a map of lambda called gamma mu of lambda, and it goes into the manifold of space-time. And then this manifold of space-time is broken up into atlases, right? Well, it has, I shouldn't say atlases, it's broken, it has an atlas. We have established some kind of atlas on the space-time, and that atlas marches us right into Rn, where we have our curve. And ultimately, the curve exists in here, and the curve exists in Rn, where it's given coordinates. So that's how the whole manifold things works. You know, this is actually a bit of a point of confusion. Everybody's, and I can understand why, there's a lot of concern about this going from here into the space-time and then into the coordinates. It's this part that confuses people. Like, what is this space-time? Because we're always dealing with coordinates. And remember, think of it this way. The assumption that space-time is a 4D manifold, right? That is an assumption of general relativity. Assumption. Assume it. Right? So because you're assuming it, you don't ever have to play around with this literal function into the space-time manifold. It doesn't really exist. We don't have some kind of abstract mathematical construction that's here, where we literally have a map here, and then we have a map here. The assumption allows us actually to sort of skip through it, because by assuming that it's a 4-dimensional manifold, we know that we can get from here into coordinates. So when we write this function, you know, this is actually not truly the right picture, because what this function is this function implies that we're going into some abstract space, that there's some map that takes lambda and gives you some kind of point in this abstract space-time manifold, which I might call M. And then I have some additional function that goes from, which would be the charts, right? That would go from M to the real numbers. But what's really happening notationally, and it's very important to understand this because all the books do it slightly differently, and it can be kind of a subtle issue. What we're really looking at is that gamma mu of lambda really is already, each gamma mu is a real number, and it is a coordinate. Which means, in principle, if we really broke this down, I would give this, I would have to say that I would have to go, that when we're dealing with the coordinates, I would have to literally say phi after gamma mu of lambda equals x mu of lambda. In other words, and this would have to be phi I, because right, there's each of these regions would be called ui. Each of the charts would be ui. So what I would actually have to say is that if I took this picture completely literally, I would have to say I have a map from the real numbers into the space-time, and then a chart from the space-time into the coordinates. And if I call this the map into the space-time, then the coordinates that I'm going to actually work with have to be the chart after the map. And that would be this coordinate. And then each of these charts, right, that chart, that even that's not exactly right, because what that really is the chart after the map is actually going to be a set of 4 coordinates, x0, x1, x2, and x3. So if I want x mu, I now need to take the coordinate function and act on this thing just to extract the one I want. So I would have to have this coordinate function, x mu, after those things to literally get what I'm after. And then that would actually ultimately equal the coordinate x mu. And it would be a function of lambda. Everything's obviously, lambda is the only real parameter there. So now the problem with all of this is that different books will go through it different ways. And they'll say, oh, we have a curve in space-time. Let's call that curve x mu of lambda. And what they're really saying is that the coordinates of every point on this curve, the coordinates of every point is given by this expression, these functions of lambda that are x mu. But sometimes we talk about x mu as the coordinate function that has to act on a set of 4 points, in which case the curve is actually given by this object, and that gives us the 4 points of which x mu peels off 1. Or we can just cut off the whole thing and say, look, we've got lambda, and we've got space-time, and then what we do is we think of space-time in the coordinates kind of blended together, and we say we've got gamma mu of lambda, and that is the coordinates, right? So we're just laying down the coordinates. We've laid down the coordinates right onto the space-time from the Rn's, right? Because this is, well, R4, because this is general relativity, right? So all the different R4s, all the different atlases, we lay the coordinates out onto the space-time, and then what we say is, this is the coordinates, right? Now some books will do this, and they'll still stick with the literal name of the coordinates. If we are calling the coordinates x0 to x3, they'll still say x mu of lambda. In fact, Meisner, Thorne, and Wheeler likes to do that. I'm not sure about, I don't remember how DeVerno did it or how Chandrasekhar did it. But you have to be very careful. Sometimes you'll see this, and that is the curve. Sometimes they'll give the curve a name. And in our case, I like to give the curve a name. But if I'm talking about the zeroth component of a coordinate along that curve, I will go lambda, 0, gamma, superscript 0, lambda equals, say, 0.5, right? That would be this point gets mapped, say, to that point right here, and the zeroth component is this thing there. All right, so that's really important. You have to understand how we're parameterizing and talking about these curves. And with that in mind, that'll establish our notations, and we will proceed. So, back to this. This lambda, by the way, could be any parameter. Any parameterization of this curve is fine. We're not going to assert that it's the proper time quite yet. Eventually, we'll get to that point. All right, so now going back to just our curve. So I'm going to now draw this curve in space-time, and the points along this curve, of course, are going to be gamma of lambda. I'll put the mu up there. Gamma mu of lambda. See, I can make a better lambda. Gamma mu of lambda will be the points along that curve. That point would be, say, gamma mu of 0, where it sort of starts. And somewhere along this curve will be gamma mu of 1. And we're not restricted to 1. Let's just allow lambda, just as an arbitrary starting point, be 0, and say it goes to infinity. That's how lambda does. There's language for spacetimes where lambda can go to arbitrarily high values, right? and we'll talk about that later, the notion of geodesic completeness. But now I have this curve, and from this curve, which is parameterized by lambda, I can make tangent vectors. I can make tangent vectors at every point along this curve. And those tangent vectors are easy to calculate. If I know this formula, I can take this derivative and I've got the tangent vector. So in, say, this point on the curve, there's a tangent space. And in that tangent space, I have the partial, well, not partial derivative, because there's only one variable here, right? Lambda is a single variable. So this is only a function of one variable. So there's no partial derivatives going on. These are just regular derivatives. D lambda mu d lambda partial mu. That's the tangent vector at that point. And the reason it's at that point is this derivative here is actually evaluated at gamma of lambda. So I can actually write that better, right? I can clean that up. It's an important point to make, right? It's a vector field. So d gamma of lambda, d lambda, evaluated at gamma of lambda, which in this case, it's that point right there. Let's call that point lambda 1. Just some subscript to show that the value at that point is gamma lambda 1, right? And then lambda 1 might be like right there. And that partial mu, that is the vector inside the tangent space that is tangent at that point. And now the temptation is to depict it like that, literally like a little tangent vector on the curve. And that's fine. Just understand that it's living in this tangent space, but it's convenient to draw it in this direction. And because everything's continuous, we are expecting to have sort of a similar collection of arrows all along the curve. Now, the point being, and that's how I'm going to draw them. I'm going to draw them like this now, just to because that's the mathematical analysis we're using. It's these little vectors that are attached to that are inside the tangent space at every little point on the curve. So what we have is sort of, almost sort of, kind of a vector field. It's a vector field in the sense that we have a vector at every point, and I want to say at every point in space-time, but that we don't. We only have vectors along this curve. Once we have a curve, imagine we had a space-time, and we had a curve in the space-time, and nothing else is part of our construction of the universe or our construction of our model. Well, that curve will provide us at least one sort of semi-vector field. It's semi because it doesn't define a vector everywhere in the space-time, right? It has nothing to say about this and nothing to say about this. But at all the points that curve actually goes through, it does, in fact, define a vector. And this is important because you may remember back from what is a tensor is we want to know what things are, if we're given a certain minimal set, in this case, a space-time manifold, right, and a curve in that manifold, if we're given that, what kind of things are automatically must be there? For example, a metric connection. If we're just given a manifold, right, we don't have a metric connection. We're not given a metric. We're not even given a connection. A manifold is just a set. You can have a manifold and put coordinates on a set, you know, in the following all of the prescriptions of a manifold, and have no metric, and have no, you don't have either a metric or you don't have a connection. And remember, you can give it an arbitrary connection, right, and you can give it an arbitrary metric, and they can or cannot be connected by the metric connection prescription. If you do have a metric, you automatically have a connection, at least one available to you automatically by a certain type of definition that we talked about before, the metric connection. But given a connection, you don't automatically have a metric. You don't automatically have any of these unless you're given to them. And that's, of course, what physical theory does. The physical theory gives us this. But if you have a curve, you do have this little vector field that comes along with the curve. And that vector field is the collection of all these tangent points. Now, you could say, well, you know, we also have a different vector field. We have the vector field that's normal to the curve at every point, right? We could kind of do that, which is, but do we really have that? Do we really have a vector field that's normal to the curve at every point? Because that gives us an idea of perpendicularity. You would have to know the relationship between this, you'd have to know the relationship between this vector and this vector that gives you sort of normalcy. Now, when we have a metric, so that does kind of exist. But if we didn't have a metric and all we had was a space-time with, if I say space-time, that really means you do have a metric that's locally Lorentzian. Otherwise, it's not really space-time. Space-time is what the real world is. But if you had a manifold and a curve in that manifold, you definitely have tangent vectors. But the idea of perpendicular vectors, that's a little trickier, and it's not an automatic gimme. So we're going to ignore those guys. And we're going to sort of accept the fact that the curve will give us tangent vectors. That, by the way, if you really unpack it, is what allows us to do this, right? Every time you have a curve, you can get a tangent vector. That's what allows us to create the coordinate basis. Okay, so given that, now we can begin to start talking about the idea of a geodesic. So we're going to begin with this image. We got to understand and imagine a curve going through space-time, just like this. That's our curve, which we've been calling that gamma mu of lambda, right? That's the coordinates of this curve moving through space-time. So see how I'm already kind of blurring it. When I say space-time, I mean the manifold modeled by a four-dimensional space-time is a set modeled by a four-dimensional manifold, and I'm now actually talking about the coordinates on that manifold, and so it's kind of a blend of these concepts, right? But it's still unambiguous. These are the coordinates of the path through space-time. And whether or not you want to throw in those charts in your head or not, I would advise you to kind of get used to doing it this way. Those are the coordinates of this path through space-time. But we're going to go to a very small part of the path, right, between this point blue and this point red. And I've blown that up here, sort of turned it and blown it up. And at the blue point, we have the tangent vector, and at the red point, we have the tangent vector. And these are defined by the curve itself, simply the formula for the curve itself, which is this thing I just drew right here. The derivative of the curve with respect to lambda. And notice I put that there saying it's a function of lambda, right? And if I want, I can actually put in lambda 1 if I want to call this point lambda 1 and this point maybe lambda 2. Evaluate at lambda 1, lambda, and then this guy over here is the same thing, gamma mu d lambda evaluated at lambda 2 partial mu. So those are the two tangent vectors. Now what's important to understand is that the tangent vectors are completely given by the structure of the curve, the functional structure of the curve. And once I know this curve, I can always calculate this. And notice I do not need, and this is what's important, I do not need the connection, right? A connection on the manifold, be it a metric connection or on any old affine connection or any connection you provided for the manifold, I do not need that to calculate this and to calculate this, right? The only thing that I need to calculate those is the curve, right? And the curve is parameterized by lambda. So that's a function of lambda only. Those derivatives are easy to calculate. I do not need a connection on the manifold. Now, let's imagine that we do have a connection on the manifold. And I'll give that connection a name. I'll call it gamma alpha beta. Well, I've used gamma already. It would normally be alpha beta gamma. So I'll call alpha beta delta, right? Except that my alpha is terrible. Not that this alpha is much better, but alpha beta delta. All right, so now we are given this. We are given this. And once we're given that, we can now talk about a lot more things. Notice, by the way, we still only have a vector field in quotes because our vector field, the only vector field we have, is the field along this line. The only vectors defined in this entire space that we've created so far are just the tangent vectors along this curve. Because we have a manifold, we have a curve, and the curve gives us tangent vectors. That's the only vector field we have. But once I say I have a connection on the manifold, actually I have an interesting object. I have the function alpha, beta, delta of x. I guess I should put it x, say nu, right? I have a function that exists everywhere on the manifold because I get a value for the connection at every point in space-time. And this is what, 4 times 4 times 4, right? There's 4 possible values for those indices. So that's 64. I have, in principle, 64 functions on the space-time. Now, we've already know that that we're symmetric in these indices, and there's a lot of things that cut this back down, but it's 32 functions on the space-time. And that function exists everywhere. I can calculate the value of the connection at this point. I can calculate it at this point. I can calculate it at this point. And I can calculate it at every point along the curve, too. So I can calculate the connection everywhere. So it's sort of a bigger deal than just the one little vector field that exists on this curve. But the most important thing it's arbitrary, right? I can have a lot of different connections on my manifold, and every one of those connections tells me how I can parallel transport a vector along a curve. So let's imagine, and I'm going to clean this up a little bit because I got a little excited about the connection. Let's imagine that I have 2 different connections. I'm going to just talk about 2 different connections. Say I'll talk about gamma, alpha, beta, delta, and then I'm going to talk about, say, not gamma, let's say, I'll give this other connection a different name. I'll call it, what's this guy? Capital Z, alpha, beta, delta. I'll call this one, say, eta, pi, sigma, something like that. You remember this is a Greek letter, right? That Greek letter, I think it's capital C, right? Xi. But, so I have 2 connections, right? And both of those connections, they're different. They're both functions on the space-time, right? X mu, and let me split them up. So, and I can pretend that the manifold has this guy, and I can pretend that the manifold has that guy. Neither one has to be a metric connection, just some connection on the manifold. And what do we know about connections? Well, they are what gives us the rule about how to parallel transport a vector along a curve. We know how that's done. So we can immediately imagine taking this blue curve, this blue tangent vector, and using gamma, we could parallel transport it to this point here, and we'll get some result, right? We'll get some result. Likewise, I could, and this, I'll call that, let's see, I'll put that with a little gamma there, showing that I used gamma to parallel transport that one. But I could do it also with this other one, right? And I might get a totally different result, right? There's no control over it, right? This could be anything. The point is the parallel transport is completely dependent on this choice. Likewise, I could move the red vector back to lambda 1 and I'd have the same problem. So the point is parallel transport from lambda 1 to lambda 2 of that tangent vector, I need something to start with, right? And the only thing that I can start with is the tangent vector. There's nothing else in the universe out there. I could make up a vector, but now I'm inventing something new. But once I have the curve, which I'm assuming is we've been given, I'm handed a vector. So I might as well play with that one instead of just inventing a new vector. But the point is now that I've invented 2 connections, I'm starting inventing things like crazy in a sense, because these guys are really powerful, and they tell me how I can parallel transport that guy. So now I have 2 completely independent things that are telling me something about vectors. One is I have a curve that creates a vector field, and as I move along the curve, the vector field changes from this blue curve to this red curve, to this blue vector to this red vector. But the other thing I can do is I can move along this curve and take this blue vector and parallel transport it all along the way using the parallel transport equation, and I can end up with a parallel transported vector. So that is the crux of what the mathematical idea of geodesic is all about. Because this curve could be a very special curve whereby the tangent vectors at every point along the curve happen to be the exact same vector you would get, or at least a vector very similar to the vector you would get if I parallel transported it by, say, gamma. But there's a different curve that would be where the parallel transport of a tangent vector along that curve using psi would give you the tangent vector of the curve. So what I'm doing is I'm looking for a curve. Well, first let's say I settle with one. Let's consider psi. I have to choose a connection. Say I take the connection psi. Wouldn't it be nice to find a curve where the tangent vectors along that curve always were very, very similar to, if not equal to, the parallel transport of the tangent vectors themselves. In other words, this curve here actually ends up being at least in the same direction as the tangent vector, if not literally the same, right? So what kind of curve would that be? Now here I'm sort of redefining. I'm redefining the connection to satisfy this curve. But what really should be going on is I should be finding a curve that satisfies that property for the connection. So ultimately, let's resketch exactly what we're looking for. So ultimately what I would like is given a manifold and given a connection on that manifold, I want to find a curve when that I take any tangent vector on that curve and parallel transport it to another point. The resulting parallel transport, which I have in green here, is going to at least be in the direction, the same direction as the tangent vector to the curve at that point. So this value of lambda, say 1, this is the tangent vector at this point, and this is the tangent vector at this point. I want the parallel transport. I want this parallel transport vector, which I'll call v. I want v to equal some constant times the tangent vector that is at that curve. And v is dependent on this, where I'm suppressing the space-time dependence, right? V is completely dependent on that and on the curve, right? Remember, the parallel transport, remember we did that whole thing where parallel transport along, say, this curve is going to be a totally different vector than parallel transport along this curve, right? Parallel transport is totally path dependent, completely path dependent. So v depends on the choice of the path and the connection. So assuming the connection is fixed, what we can imagine doing is changing a path of a curve until it's finely tuned so that this is a true statement. And that curve would be called a geodesic curve. And even better, we can even fine-tune that and fine-tune the parameterization, which is sort of an arbitrary thing. And we can make it so that the green vector is always exactly as long as the red vector. Right? We can not only make it so that they're pointing in the same direction, but we can make it so that they are the same length. And that is, actually at this point, it's almost easy to do now that we understand what we're looking for. So let's do it. All right, so this will be our construction. There's our fixed connection. This is the manifold n. Here's a little segment of the curve. I guess curve, of course, goes on and does other things. I have to make the segment. I have to make the segment a little bit arced. Otherwise, the tangent vectors are pointing along the same line. Like if I did a straight line, I would have a tangent vector like this and a tangent vector straight along the curve. It's a little bit clouded, so I kind of make the curve arced. But remember, we're talking about points that are so close together that it literally kind of looks, it limits to something very similar to this, to being a straight line. But we're going to leave it arced for right now. And we're now going to execute the construction that develops this requirement. So how do we begin? Well, the first is we will draw our tangent vector at this point, which I'm again putting it in the plane of the space-time, just like you have to understand that this is in the tangent space. And then we're going to talk about moving it from here to here. We're going to execute that. Let's execute the parallel displacement first. We know the tangent vector. We know the formula for that, right? It's d gamma lambda d lambda partial mu, right? We know, I guess with a mu here, we know what that is. So that's easy to calculate because we're assumed we're given the curve. I guess I should write that in there. We're given the curve lambda. Well, this will be, that point will be lambda mu lambda 0, and this point will be gamma mu lambda 0 plus some little increment delta lambda, and I have that depicted down here. The second point is delta 0 plus is lambda 0 plus little delta lambda. So that's the coordinates of this point. These are the coordinates of this point. These are the coordinates of this point. This delta lambda is this increment from the parameter value of that point to the parameter value of this point. The parameter value of the blue point to the parameter value of the red point. So now the question is what is the parallel transport expression? So we know. So now let's look at the components of the vector, the tangent vector at that point. The components, and this should be absolutely no surprise. D lambda, that evaluated at, well, actually what I should be writing here is, let me do a little erasing here. We'll assume, right, it's d mu of lambda, right, evaluated at lambda 0. That's the tangent, that's the components of the tangent vector at that point, right? If I wanted to do the full vector, I would add in this, but I would add in the vector basis, which in the coordinate basis are these differential operators. But we're going to omit that because Denverno doesn't use it, and neither does Chandrasekhar, because they're classical texts, right? And my whole grievance with classical texts is the absence of basis vectors. But the irony is once you fully understand the whole process in the presence of basis vectors, it's very, very easy to realize, oh, I don't need those basis vectors. And in fact, that's exactly the advanced logic that these books use to omit them. The problem is the students aren't immediately familiar with that logic, and so it just looks like a big mystery. At least it did to me. Anyway, so these are the components. These are the components of this tangent vector here. So now we will remember our formula, our definition of the connection coefficients in one context, for our formula for the parallel transport. And the way we express the parallel transport is we would say that the change in the components, and I think Denverno puts a bar over it, of a vector x mu. So these are the change in the components of a vector x mu, and presumably this vector x mu is at, say, this point here. So that point here you have a vector x mu, and in this case it's the only one vector is in sight, it's our tangent vector. But speaking in general terms, if we had a vector field x mu of x, there's some vector at this point, and we're interested in the change in the components of that vector when it's parallel transported to a nearby point. But but the change in that in the components of a vector x mu under parallel transport is equal to the negative of alpha beta eta x beta delta, and I guess it's this curve gamma, so I'll call it delta gamma because it's the change in this curve, bit delta gamma eta. Let's see, I'm going to do some erasing here, right? So this term is the change along this curve, right? That's delta gamma mu, the change in the coordinates along that curve. This is the value of the vector at this point, so that's x beta of lambda 0. This is the connection at that point, so that's actually alpha beta eta at gamma mu lambda 0, right? Because remember, this is a function of space-time, so I need 4 coordinates in there. Well, that's this point. Well, the coordinates of that point is this, so I put that in as the argument, and then out comes the connection at that point. So presumably I know that. So everything on this side is knowable as long as I know the vector field. So what I'm going to do is I'm going to do the obvious thing, which is to let me increase the thickness of this so I can erase this a little better, a little quicker. So I'm going to do the obvious thing, which is to replace x in this formula. I'm going to replace x with the tangent vector itself, right? So x mu, I'm going to replace it with dx, d gamma mu, and I'll suppress the lambda, right? We all know that gamma mu is a function of lambda, right? I mean, that's what it's all about. Well, that we have gamma mu of lambda, right? That's gamma mu of lambda 0, but it's a function of the parameter lambda. So if I make that replacement, then I make that replacement right into here. And what'll that give me? Well, let's do it. I'm going to take this formula and we'll move it down here. Right, we'll move it here. And we'll now write the new formula. We'll write d gamma d lambda equals minus alpha beta nu d gamma beta d lambda delta gamma nu, like that, eta. So then we need to make our substitution for this guy, right? How does that guy look? Well, interesting, that guy is this displacement along this curve, right? So that value is actually pretty easy. It's actually, we're going to approximate it by the tangent vector at this point here. We're going to approximate the change in these coordinates, this delta gamma eta, by just moving in the direction of the tangent vector. Now, in the drawing I have here, this makes no sense whatsoever because that's a really bad approximation, right? But the idea is as this point gets closer and closer, that approximation actually gets to be better and better and better. And we do make that first order linear. It's essentially a type of Taylor expansion type of approximation. So what is this thing? Well, this is going to be the tangent vector, d gamma mu d lambda, and then I trade this for a small increment of the parameter, right? And that approximation I can put right here into this formula, and I do that by erasing this, and I write d gamma nu d lambda delta lambda. And this is an expression for how the components of the velocity at lambda 0, right, the components of the velocity at lambda 0 change by this quantity. And this quantity is completely calculable. This is calculated at lambda 0, by the way. That's calculated at lambda 0, right? We know that because the second one's calculated at lambda 0 because we're literally using that tangent vector at lambda 0 to make the approximation. And this one is calculated at lambda 0 by the definition, by this definition up here, right? That should be at lambda 0. And this is the change. So this is the change in the components, but this is evaluated at lambda 0. And so this ends up being an expression here for the change in those components. So now with that, I'll take that expression and move it to a fresh screen. And now what is the value of this vector parallel transported over there? Well, it's the components here plus the change in the components that we just calculated. So how does that look? So this is what we have. Now we know what the change in the components are. It's this thing. So the new vector, the components of the vector at the red point, right? So we have the red point, we had the blue point, we had the line between them, and we took the tangent vector at lambda 0 point, this is at lambda 0, and we parallel transported it here. This parallel transported vector, it has components. And the components of that parallel transported vector are the components at this point plus this difference. And this difference was defined through the connection coefficients, as long as it's a small increment. And so this expression here is an expression for the components of the green vector. And we know everything here, right? We know we can calculate this because this is just the vector. This is the vector components here. We're sort of given that. This we know, presumably, because we know the connection on the manifold, function of space-time, or 16 or 32 or 64 functions on the space-time. This is just the same vector here. That and that are both the same vector components that we had at the blue point, and this is your amount of interval between the 2 points, the parameter, amount of parameterized interval between the 2 points. So this now is the components of the green vector. Now, had we been just doing our study of covariant derivatives, we would have then considered the vector field associated with this velocity field here, which would have been this the tangent vector at the curve would have been there. We would have talked about the difference between the two, and then we would have used that to develop the idea of the covariant derivative. But we're not doing that this time. Well, we are in some sense, but what we're saying is that, no, this curve is such that it kind of goes like this, and the tangent vector at that point is in the same direction as that. But now at least we know what the parallel transport components are. So now we take those and we're going to compare them to the tangent vector at the new point. All right, so what is the tangent vector at the new point? Not difficult. The tangent vector at the new point is, let's see, how are we going to write it down? Well, first of all, this new point here, right, is gamma mu of lambda 0 plus delta lambda, right? We all agree that that's what that point is. Then the tangent vector is this thing plus delta lambda. And we can then write that the tangent vector d lambda evaluated at the point lambda plus delta lambda, right? That has got to be the tangent vector at lambda 0 plus, are you ready for this? It's the second derivative of the tangent vector at lambda 0 times the small increment delta lambda. And that's just the first order change in the components of the tangent vector, because this is the vector component, the mu component at lambda 0. Well, that's a function of space-time. We take its first derivative, which, because it's a tangent vector, ends up looking like a second derivative. Whoops. Ends up looking like a second derivative. And but the second derivative is just the first derivative of the function that we're taking the small incremental change in. And we multiply it by the small increment of the independent variable. And this is the components of the tangent vector at that point. And of course, this is all a linear approximation, right? So we're definitely demanding small increments in space-time here. So this is the components, well, these are the components of the tangent vector at the new point, and we can calculate everything, because remember, we know gamma, as I've said many times already, we know gamma, we know how to take its derivative, we know how to take its second derivative, and we can multiply by a small increment. Okay, so the point is for our goal of this, for this parallel transported guy to have this relationship of being in the same direction, we know that these components here and these components here, right, the components of the parallel transport of the tangent vector at lambda 0 compared to the actual tangent vector at lambda 0 plus a small increment, those two have to be related by a constant. So now we will make that relationship formal. And so here I have established the equality. I went offline for a second and wrote it down. And so this is the tangent vector at the point lambda 0 plus delta lambda. And this is the parallel transported, vector, the parallel transport of the tangent vector at lambda 0, parallel transported to the point lambda 0 plus delta lambda. And we want them to be equal up to a constant. And that constant can change all the time. So we have to say that the only thing it could change with respect to is lambda, because it's going to be along this curve. The parallel transport's always along the curve. So we can say that the constant varies as a function of space-time, but we're always along this curve, so the functions of space-time are all dependent on lambda ultimately. So we can say that this constant is a function of lambda. And this expression here is ultimately where our geodesic equation is going to come from. You can almost see it, but there's still a little bit of thinking to do. In particular, we have to think a little bit about the nature of this constant c in various limits. In particular, the limit where this is actually 0, like if you don't do any displacement along the curve, then this parallel displacement is 0, right? It doesn't change, right? The components of the tangent vector, by the way, everything's evaluated at lambda 0, even if I suppress, I didn't try to squeeze in a lambda 0 in all of these places, right? Because it's just too much of a mess. So let me get rid of those. But they're all evaluated at lambda 0, right? So where was I? So the idea is this left-hand side, if you do no parallel displacement at all, right? If this equals 0, that goes away. And what that's telling us is that the tangent vector, which I guess now I actually do want the lambda 0. The tangent vector evaluated at lambda 0, its components don't change because you haven't moved anywhere, right? So this side just ends up being some constant times something that's not changing at all, right? Or it's a constant times the actual components of the vector unchanged. This side, if you take away lambda 0, you get the same thing. So you end up with this equals this, and of course, in that case, c has to equal 1, Okay, so C has to equal 1. Then, what about, there's another limit here to think about. Well, maybe not. Maybe that's it, actually. So the point is that when lambda goes to 0, C has to equal 1. So we can rewrite C in pretty good generality as let me lift this up, and C we're going to replace with 1 plus some constant. I guess I'm gonna change. This is a different C, right? Some constant C delta lambda. If I replace C with this, oh God, that looks so bad in black, in red. Okay, that's better. So if I replace this constant with a constant of this form, 1 plus C lambda times delta lambda, then in the delta lambda equals 0 limit, this term will always go away, leaving 1 behind, which is exactly what we need. So that equals that. So this is actually the form of this constant, right? It forces that constant to have the property that when delta lambda goes to 0, you have the right limiting behavior. Now notice this C is not the same as that C. This C is literally this whole thing. So I'm basically renaming C here a little bit. I guess to do good I should probably put a C prime there. Or actually what I'll do, just to be consistent, I put the C prime here and then get rid of the prime there. Because that's how, essentially, that's how Deverneau and Chandrasekhar's books like to do it. And just to make our algebra a little faster, I'm going to call this gamma dot mu. This should be a square here, right? And then this will be gamma double dot mu, and then I can write gamma dot mu plus gamma double dot mu delta lambda, where everything's taken at lambda 0. All these derivatives are evaluated at lambda 0. That equals 1 plus C of lambda delta lambda. So make a bracket here. I guess I'm doing brackets now. And then this is a bracket gamma dot mu minus capital gamma mu beta eta gamma dot eta delta lambda. Okay. So from that expression, we will just crunch the algebra and we'll end up with essentially our geodesic equation. Here's the first step where I just basically expanded the right-hand side, right, using this faster notation to keep things a little quicker. And then the next step will be just to isolate the second order term here. This second order term, we're going to isolate it on the left side. So we're going to subtract this from both sides. So after we do that, basically what we're doing here is this guy here and that guy, they just cancel, right? I subtract that, I subtract the first derivative from both sides, and those two terms cancel. So all that's left are these guys, which is what I've reproduced here. Then we just divide through by this delta lambda, which erases that there, erases it there, erases it there, and it turns that into just first order change. And so now I have the second derivative of everything equals this stuff here, right, multiplied by, and only one term has this small increment, but that's screaming towards 0, so, and everything else is constant, so we can actually get rid of that because we basically take this into the small delta lambda equals 0 limit. We're going to end up with this final expression here. And what is that expression? Well, I shouldn't have boxed that quite yet, I guess. Let me unbox that. It should be gamma double dot plus mu beta eta beta eta, that's the worst eta ever, equals c of lambda. Oh God, see, the problem is c's look like parentheses, so I always screw them up. C lambda, like that. And this is your geodesic expression, right? This is the geodesic equation. This guy is the geodesic equation. Now, normally we're used to this being equal to 0, right? So we have a little more work to do to prove that, and we'll do that in our next lesson. But this is basically a statement of the fact. It's basically a statement of this fact. If this is going to be true, if you're going to be able to parallel transport a tangent vector to a curve such that the parallel transport to any point is in the same direction, as the tangent vector already at that point, if that's going to be the case, then this curve must satisfy this differential equation, which, just to make contact with what the way we've been writing this, gamma mu beta eta d gamma mu d lambda d, oops, not mu, d gamma beta d lambda d gamma eta d lambda equals some unknown constant c. This is not a lambda dot here. That's not a lambda dot, in case it looked like one. C lambda dot. Whoops. I'm doing d gamma mu d lambda. So this is in sort of the clear form that whatever curve satisfies this behavior, this geodesic behavior, it must satisfy this differential equation. It's actually four differential equations, one for each value of gamma, right? Each value of gamma is going to give you a differential equation. So there's really 4 of them, right? These tie up. These are dummy indices, so they go away, but these tie up. So there's 4 different differential equations that are the geodesic equations. And the fact that this side is non-zero can be directly traced to the fact that we're allowing these parallel transport vectors to not be the exact same vector as the tangent vector, but off by some multiple, right? And what we'll see in the next lesson is we can always get rid of this and make this equal to 0. All right? So in the next lesson, that's what we'll do. We'll do the reparameterization of this curve in order to eliminate this right-hand side in red. All right, see you next time.